questions, concerns, etc. before we get started today? Yes.
What are we doing in lab this week?
This week is more cannons. We're going to change it up a little bit. Last week you would fire from the table down to the ground. This week you're going to do two shots. One where you're firing across the table to the same height, and you're going to figure out two different angles that create the same effect. And then the second one, you're going to fire up from a stool to the table rather than firing down.
We had a lot easier time this one than last week.
Really?
Yes.
Okay, good to know.
I don't think so.
It does kind of depend on your relationship with math.
I mean, we got out there a lot faster this time.
Okay. Well, results may vary, but at least for today and for Friday, I'm going to be there making. Your instructor will always make sure you get through it, however long it takes you. Anything else on your minds here at the start? Alright. Last time we began looking at Newton's laws and force. These laws describe force and also mass and acceleration. Quick review, picking up from where we left off. First law is the law of inertia, and it says that matter is lazy, and whatever it is currently doing, it wants to continue doing indefinitely until something forces it to change. Second law, force equals mass times acceleration. Third law, for every action force, there is an equal and opposite reaction force. Again, we are going to constantly refer back to these, so you do need to integrate them into your math and your thought processes, especially the second law when it comes to math. I want to point out that I do ask a question about the laws on test 1, which is in less than a month now, just keeping it on your radar. The way that I word that question is not, I do not ask you to write them down verbatim from memory. What I ask in the test question is I want you to be able to pick the laws of motion out of a lineup and number them accordingly. What I do is I list 5 statements, 2 of which are not laws of motion. You have to pick out of the 5 which ones are and then number them correctly. So again, you don't have to recite exactly this from memory, but I do want you to understand it and be able to comprehend what the statement tells you and know which law is which in terms of the order they're numbered in. Sound fair? Okay, light nodding, good to see. Now, to resume where we left off, we're going to apply this information to some sample questions. First one, I'm going to give you guys just some time to work on it either on your own or amongst yourselves with your team, with your classmates, before I tell you how I do it and then move on to the next concept. So here we have a 500-gram box. I'm kind of envisioning this as a 4-direction tug-of-war match as seen from above. 500-gram box being pulled by 4 different forces in 4 different directions, and I'd like you to tell me the component form of A, the net force acting on this object, and B, the net acceleration of this object as a result. Take a couple minutes, look this one over, and let me know if you have any issues with it or arrive at an answer, and then we will look at how I recommend doing it. answers, conclusions, or issues? Yes?
Do you want me to answer?
If you have one and feel confident sharing.
I think it's 675.
Almost. You know what, let me actually check something real quick. Yeah, if instead of components, I wanted to know the magnitude of the overall force vector, it'd be about 56.
Are you not supposed to just add them all together?
No, and I'm glad you asked because I do want to discuss that. So, what I've asked you here is net force, and the definition of net force, the definition of net anything really, is all of the individual things of that type present added together. However, in this specific case, I would not literally recommend just adding all of those numbers together because they all point in different directions, both positive and negative within two separate axes, meaning some of them work against each other. Before I go further with the numbers, looking at how these forces all point, what direction do you think this object is going to start moving in, looking at these numbers?
Fourth quadrant.
Yes, fourth quadrant. Down and right. I said left or down and right. More down or more right?
More right.
More right. So east, southeast. And I'm bringing this up now so that we can set that expectation and compare our answer back to it later. All these four things are working against each other. So rather than just pile all those numbers together into one big line of addition, I am instead going to orient them vertically and in terms of their components, like I demonstrated with displacement vector addition last week. So, starting at the positive x-axis and rotating quadrant-wise around, how is that first vector, the 250, is that x or y? X. What would its y component be? Zero. That vector points entirely along the x-axis. It doesn't have a y component. So, in component form, it would be 250, 0. Now for the 100, what axis does that point in?
Y.
And what would its x component be?
0.
Very good. So already we see that the numbers do not all just add up into one big number. Continuing on, we got 200 newtons in the x-axis, but it points in the opposite direction as the 250. Meaning, whatever sign you put on this first one, you got to put the opposite one on the 200. And likewise, the 125 points opposite the 100, so whatever sign you put on the 100, the 125 needs the opposite. So again, not only are there two different axes, meaning some of these numbers just don't interact with each other at all, some of them work against each other, and you have to factor that in. So if we add x with x and y with y, we get 250 plus 0 minus 200 plus 0. For 50 in the x-axis, y is 100 plus 0 plus 100 plus 0 minus 125, so negative 25 in the y. So that is the component form of the final answer. Those would form the legs of the overall force triangle as represented here. Which again is more left than down. More right than down, excuse me. Questions thus far? All right. Keep in mind, force is a vector. You do care about axis and you do care about direction within that axis as a result of that. Now, We could find the hypotenuse and determine a magnitude and direction for that force, but that's not what I am asking right now. Instead, I want us to find the net acceleration based on this component form of the force. So, if you know a force acting on a mass, how do you find the resulting acceleration of that object?
Well, we have the mass, we have the force. All we have to do is divide the force by the mass.
Yep. Good old Newton's second law. And this formula does specify net force, which is exactly what we've already found. That is the net force, and that's going to cause net acceleration as a result. The one thing to note before moving forward is that our component form of our force answer has two parts to it that don't inherently mix. So we have to do this once for the x and once for the y if we keep our answer in component form. So net force in the x-axis is positive 50. Then for the mass times acceleration part, we just plug in 500 and we're good, right?
No.
No, what's the catch?
Kilograms.
Very good. How many kilograms is 500 grams?
25.
Did someone ask a question? Or did someone just...
We just said it at the same time.
Okay, fair. Apologies. Yes, 500 grams is 0.5 kilograms. Anytime you see grams, you're going to want to auto-convert that to kilograms. And as a result, the answer is going to get bigger rather than smaller. That's going to be 50 divided by 0.5. So the x component of our final acceleration is going to be 100 meters per second squared. And we just do the same thing in the y, except that net force was negative 25 instead of 50. Mass stays the same though, because mass is a scalar, it doesn't care about axis. So AY is negative 50, negative just meaning down. So those are the legs of our force vector. And that's all I asked for, so we're just gonna stop it there. There it is written in coordinate point form. How's this one feel? Concerns, objections? All right. Main takeaways I wanted you guys to get from this are: one, force is a vector, so you care about both axis and direction. You can treat it like the same vector addition we've been using. And two, kilograms. Cool? Uncool for anybody? You're allowed to tell me. All right. Now, we're going to be coming back to the laws of motion throughout the entire semester. And the next thing I want us to work on in relation to them is looking at different types of force, where they come from, how they're commonly measured and used in this class, and how they then relate back to the laws of motion. We already talked about a few different types of forces. We're just going to kind of define them one at a time and show some examples of where they show up. No matter what we call an individual type of force, though, all forces still inherently behave the same way. They still exert a vector force on things. They still push or pull in a direction. They still act on objects with mass to cause acceleration. So no matter where a force comes from, it still behaves all these laws, and all forces acting on something still add up together regardless of the origin of that force. But it's still important to discuss the different types of forces and where they all come from, because there's a lot of weird ones out there, if I'm being honest with you. As an interesting example of some specific types of force, most forces are divided up into two categories. You've got contact forces, which is the only type you can consciously exert with your body. You physically touch something and exert force through that contact. But there also is a separate category called field forces, which is where the force does not need contact in order to happen. The premier example of this is gravity. Note, gravity pulls on this marker even when the marker is not touching the planet. So that's one example of different types of forces and how we categorize them. Speaking of gravity, though, that's the first one that I wanted to give you a definition for, because even though we've been discussing it, I don't know if I gave you a written definition yet. Gravity is a force. I want to make that clear. It is a force that causes acceleration, but it is itself a force. And the way that we calculate that force is with this formula over here. It's a slightly modified version of Newton's second law. Fg stands for force gravitational. It's just F with a subscript of G. There's going to be lots of different types of force, and most of them are going to be designated as capital F with a subscript to better describe what subtype it is. But they're all still forces, and the capital F indicates that they can be mostly used in all the same places. Force of gravity specifically, though, we calculate the force of gravity acting on an object by taking its mass in kilograms and multiplying it by a very specific acceleration, that being the acceleration of gravity on planet Earth. This lowercase g stands for acceleration of gravity, and is again referring back to that gravitational constant we started using a few weeks ago for falling objects. That value is still negative 9.8 meters per second squared. That is the rate at which objects fall on Earth in the state of free fall. That happens because the force of gravity is pulling down on objects with mass in order to induce that acceleration. So the technical order of things is the force of gravity acts on something and causes the acceleration of gravity. But what we usually will do is we will use the acceleration of gravity in that formula to work backwards and figure out what the force of gravity is on the unique object that would cause that acceleration. Objections so far? Okay. Some notes, some minor details here. This formula is partially meant to represent the fact that mass and force of gravity are not the same thing. A synonym for force of gravity is weight, which means that weight and mass are, again, not the same thing. Forces, by definition, are vectors. They point a direction. On Earth, gravity always points down towards Earth's core. And that the strength of that force depends on the mass of the object, and it depends on the strength of the planet's gravity. Mass, meanwhile, is separate from gravity because it's just the amount of material inside of the object in question. It's a measure of how many protons, neutrons, electrons are crammed inside of it. That is not technically its weight, and for that reason, mass is not a vector. It's a scalar. It doesn't point anywhere. And mass stays constant even when you change planets. If you go to the moon and want to calculate your weight there, this number stops working because this number is specifically Earth's acceleration of gravity. I will label that. Earth's surface only. So if you leave Earth, that negative 9.8 stops being true and something's weight changes, but its mass doesn't. It's a nitpick of mine, but it's something that I want to make clear. Even though in the UK they use mass as if it was a unit of weight, it does get the right point across, it's just technically wrong, which is the most annoying kind. One other point in regards to this formula. This right here, G equals negative 9.8 meters per second squared. This is not the force of gravity, and it will never be the force of gravity, even if you're trying to find the weight of a 1 kilogram object, and this formula tells you that 1 times 9.8 would be 9.8 newtons. because this is an acceleration. It's measured in meters per second squared. If I ask you, what is the force of gravity, and you write negative 9.8 meters per second squared, I will be sad. I bring this up because that is a test question, by the way. How do you calculate force of gravity? That's the answer. This is not the answer. This is part of the process. I think I was rambling for a sec there. Questions? Concerns? This ends the chapter of me nitpicking about gravity calculations. Tangent point, stay hydrated, especially if you talk a lot. So, gravity is a very important type of force. We're going to come back to it often. I will note again, this number is only true on Earth's surface. If you leave Earth, this number starts dropping. And if you dig deeper into the Earth, that number starts increasing. Because gravity, the strength of a planet's gravity depends on your proximity to its core. If you get higher up, like you're heading into orbit or towards the moon, that number goes down. It doesn't vanish though. There is gravity in space, even on the space station. They appear weightless, but it's not because there's no gravity in space, it's because they're falling. Meanwhile though, if you dig further down into the Earth, you get closer to Earth's core, meaning gravity is stronger, and that number increases. So that number, the negative 9.8, is pre-described as Earth's surface level of gravity. You can automatically assume that formula, that number is true if a problem specifies Earth's surface or doesn't specify anything other than Earth's surface. But if you go digging deep enough, gravity increases and you will be crushed by tremendous forces and turned into magma. So don't do that. Now, the other type of force I want to define rather, is normal force, which we did mention on Monday, but I wanted to make sure you saw a written definition. We brought up normal force before in our examining of the forces acting on stationary objects as they sit on tables. For example, if this is the diagram of our object, Earth's gravity pulls down on it, whereas normal force from the surface points up on it. Normal force is the force that a surface exerts back out of itself as a response to something pressing into it, which means that normal force is entirely a function of Newton's third law of motion. Tab back to it real quick. That's not the right slide. Tab back to the laws real quick. Third law states, for every action force, there is an equal and opposite reaction force. In this context, whenever an object or a person, in the case of you and your chairs, presses into any surface, that surface is going to push back up on the first individual in the opposite direction. So, for anything sitting still on this table, because of gravity, they all push down into the table, and as a direct reaction to that, the table pushes back up on the offending items. This is true of any surface, and this is true anytime an object is either sitting still on a table or on the ground. It's also true if you're just moving horizontally across the ground. As long as you are not jumping up or falling through the earth, the normal force tends to equal and opposite with the force of gravity. They tend to cancel out, and as a result, you remain on the ground rather than, again, falling through the dirt. So, general rules: if you are being supported by whatever you're on, this normal force upwards that is acting against your force of gravity, adding to zero, and as a result, you remain on the surface rather than, again, anything else weird happening. Some finer points that I want to point out are: one, why we call it normal force. Did I mention that on Monday? Why we use that term for it? Okay, just checking. If it helps for you to think of normal force as something normal, average, common, mundane, that is totally valid, because frankly, it is normal, average, common, and mundane. It is everywhere. There's always a normal force acting on you as long as you are being at least partially supported by a surface. The only time there isn't normal force acting on your body is if you are literally falling through the air, or flying, I guess. But as long as you are touching a surface, there's a normal force. So yeah, it is normal. It's a normal thing. You can think of it that way. But the technical reason we call it that, the reason why physicists and mathematicians gave it that name in the first place, is because of the math definition of the word normal. Because mathematicians decided that we needed at least 3 different synonyms for the word perpendicular. Mathematicians use normal as a synonym for perpendicular. The other synonym is orthogonal. I don't know why. We call it that because if, as an example, you are exerting a force downward into flat, level, horizontal ground, note that this force that you press into the ground with, usually because of the force of gravity, is perpendicular to the surface of the ground. They are oriented 90 degrees apart from each other. And likewise, since you acting on the ground means that the ground acts back on you in the opposite direction, the ground, rather than pushing straight down, will push straight up, which is, again, perpendicular to its horizontal surface. All normal forces are, by definition, perpendicular to the surface that creates them. This is why you, sitting on flat ground and sitting on mostly flat chairs, have a normal force that points up and counteracts your gravity down. But because of this interaction, you can get normal forces that don't point up, as long as the surface itself isn't oriented horizontally. For example, I'm leaning against the vertical wall. What direction is the normal force the wall is exerting on me? Yeah, perpendicularly out of the wall, which is horizontal in this case. The whole scenario has just been rotated by 90 degrees. Normal force is always perpendicular to the surface that creates it, however that surface is oriented, and for that reason, the mathematical reason, it's called normal force. Sound fair so far? Okay. Let us quickly utilize these definitions in another sample question so that you have some math for it in your notes. We're going to take a 100 kilogram box and sit it on a table. So I'm just going to start with a free body diagram of a 100 kilogram object. Gave you kilograms this time, so no conversion required. And we're just going to sit it perfectly still on a table. So, first question, what is the net force acting on this box? 0, exactly. We know this because if it's motionless, its current velocity is 0. If its velocity remains 0, it is by definition not accelerating. And according to Newton's second law, if it is not accelerating, net force is 0. So the sum of all the forces currently acting on it must add up to 0. The box is in equilibrium, and that's why it's not going anywhere. Questions about that principle? All right. Moving on from that, rather than looking at the net force, let's start looking at individual forces. What is the magnitude and direction of the force of gravity currently acting on this object?
Negative 980 newtons.
Yep, had at least two people indicate that somehow. Very good. That said, I will demonstrate where that number comes from. The way we're going to find the weight of anything on planet Earth is using this formula here, Fg equals m times g. So we take our mass of 100 kilograms, multiply it by negative 9.8, and that will give us a force of gravity of negative 980 newtons, the negative just meaning down. I'll add that number to our picture. So that is the non-zero weight of this object. There is definitively at least one non-zero force acting on it. Why does the object not just fall through the table then?
Because the table's providing positive 980 newtons.
Correct. The table would support the object with a normal force. The next question then is, what is the magnitude and direction of that normal force? To examine that, I'm going to draw your attention to the fact that we know the net force on this object is 0, and the definition of net force is just the sum of all the forces present. So whatever forces are present, they all add up to 0. And if this object is not falling through the table, there must be some amount of normal force present. So that is the second of the two forces that must be here, adding up to 0. There's not really a more official formula for normal force than that. It's just all the present forces adding up to something, adding up together. Taking care to keep your axes designated and distinct. Now, whenever two things add up to 0, you can usually draw a pretty quick conclusion about their relationship to each other. N minus 980 is 0. Therefore, n is going to be positive 980. Exactly equal and opposite in order to keep this object on the table and not falling through it. Feel good so far? That one feel straightforward enough? No real complications? All right, time to add some complications. One other thing I'd like to point out about normal force is while it is often equal and opposite to gravity, it is not by definition equal and opposite to gravity. Normal force doesn't care about gravity. It just cares that something, the object that is creating the normal force, only cares that something is pressing into it and it's going to push back as a counterattack. To demonstrate this phenomenon, we're going to take all this nice work we just did and mess it up by adding a second box. We're going to take our 100 kilogram box and add a 50 kilogram box physically sitting on top of it. Now, my question to you about this scenario, from the 100 kilogram box's perspective, does its weight change?
No.
No. That's because weight is a function of this specific object's mass and the planet this object is parked on. Neither of those change when you sit something on top of it. So this object's weight remained constant. So I'm going to redraw a new free body diagram. So this is just the physical picture, box and the mass on top of it. This is going to be a drawing with all the force arrows on it. We've still got force of gravity down, and that didn't change. The box still weighs 980 newtons downward. And there's still some normal force acting on this thing. What we actively changed by adding this other box is we've added something in that's going to create even more downward pointing force on the first box. The first box's weight doesn't change. There is now a new source of downward pointing force, that being the weight of box number 2. Now, what would the weight of a 50 kilogram box be? If you've already found that of 100.
Negative 490.
Very good. So box 2's weight is negative 490. That's just 50 times negative 9.8. It's half of the first box's weight because it's got half the mass. That is now an additional downward pointing force pressing into this box. So it's another force on the box that needs to be balanced out to keep the box in place. Yes?
Won't the 100 kilogram box also be providing a normal force on the 50 kilogram box?
It will, but
But they
that
can't
this
see.
is a diagram of just the forces acting on the first box. Free body diagrams are always meant to represent forces acting upon the object in question, rather than the forces the object itself exerts back. So there would be a separate picture for the 50 kilogram box that does have a normal force from the first box up on it. You are absolutely correct. The rule for free body diagrams is they show the forces that act upon the object being studied. You're correct that force exists, it's just on a different picture. Does that answer the question? Okay. So this picture is just the forces acting on the first box. And originally there was 2, but now there's 3. We've added a new force acting upon this object. The weight didn't change, we just added another negative force on here, and that means that normal force has to get bigger to compensate. Because the table has to support more weight now. The table doesn't really care why the number increased. It doesn't care what we placed on top of the first box. It just cares that now there's more force being exerted into it, and now it has to push back harder to make up the difference. And so rather than 2 forces adding up to 0, now it's 3. Oops. Oh yeah, sorry. Net force equals normal force plus the weight of the first box plus the weight of the second box must add up to 0. So by definition, normal force and the weight of the first object can't always be equal and opposite, because now there's 3 things that add together to cancel out. And 3s don't really work quite as equal and opposite. Like, one thing can't be equal and opposite if 3 things have to add up to 0. So n minus 980 minus 490 equals 0. Therefore, the new normal force is about 1470. Bless you. The table has to push back harder to make up the difference, even though nothing about the first box's essential attributes changed. The first box is the same, it's just now under greater levels of force. How's that feel? Once again, my point here is that the normal force is now no longer equal and opposite to gravity. It's still opposite, but it's not equal anymore. That's because the table doesn't care why it's being pressed into. It just cares something is pressing into it even more than before, and now it's got to increase the amount of effort it has to exert. And the same but inverse thing happens if, rather than make the situation heavier, you try to make it lighter. So, slightly related example. If instead of placing that extra box on top, let's say that, it's moving day, I walk up to this box and I try to lift it up. Now, 100 kilograms is frankly about my mass, and therefore the 980 newtons is about my weight, and if there was just a second version of me sitting on this table, I couldn't pick that up with my arms. All I can do is exert this much force, 400. That's not enough to actually lift this thing off the table. So I'm not actually going to get anywhere. I'm just going to sit there and strain and look kind of embarrassed, if I'm being honest. But something does happen. The box doesn't lift, but something does end up changing.
The normal force exerted by the table.
Correct. So I'm going to make a new picture. Again, these arrows just represent the forces acting on the box, not the forces the box exerts. Its weight is still unchanged, so that's still negative 980. And there's still some normal force, but I'm exerting a 400 Newton force upwards. Again, I'm not lifting it, but I am kind of relieving the effort of the table. If I'm partially lifting the box, the table's not going to have to work as hard, right? It's kind of like if you're carrying something heavy and having a really bad time with it, and then your friend notices and rushes over and helps lift the box. The box's weight is the same, but more force upward has been added, and you don't have to work as hard. Same is true for the table. If I'm even partially lifting upwards, it doesn't have to bear the full weight of the box anymore. 980 minus 400, the new normal force would be about 580. And as a result, the table doesn't have to work as hard, is under less stress, and is less likely to break. Oh, never mind, sorry. So once again, a different scenario where gravity and normal force are not the same number. This can be kind of a weird scenario to envision. I have two cases where this might have come up in your life that I want to highlight. I assume I'm not the only kid that did this. Students in the previous sections of this course agreed. When I was a kid and I saw a bathroom scale anywhere, I would stand on it and then I would immediately look for a nearby sturdy object and use it to press up and down and mess with the number on the scale. Does that sound familiar? So when you're standing on a scale and you say, grab a counter for leverage, you can pull down on the counter and press your feet harder into the scale and the number increases, right? Exactly the same as this. Because scales don't tell you weight. Your scale doesn't know how many atoms are in your body. It doesn't actually consciously know the gravitational strength of this planet. All a scale tells you is the normal force it's exerting back on you. All it knows is the effort it is going through. That's all the machine is designed to do. Scales just tell you normal force, and that's why you can press down harder into them to increase the number, even though that doesn't change the weight of the human standing on them. I still have the same amount of matter in my body, and that didn't magically increase the strength of gravity of the planet, right? So, using the counter to leverage down harder into the scale increased the normal force that was needed for the scale to hold me up, because I was putting more force into the scale, and the scale didn't care what the source was. The normal force just increased to counteract the lump sum of what was being directed into it. And the inverse is true too. You can use the leverage of the counter to lift up slightly and the number drops. Scales don't measure weight, they measure normal force. Normal force is not always equal and opposite to gravity. In fact, there are some times where normal force and gravity don't even point in the same direction. See again when you lean against a wall. Because gravity still points down, even when the wall you're leaning against is vertical and the normal force therefore points sideways. The normal force is kind of weird, and that's why we're gonna pay careful attention to it as we work some weirder examples in the coming weeks. Questions? Anyone need anything before we break for the day? That'll be on the test. Let me know if you need anything. Have a great day. Have a nice lunch. I'm rambling. See ya.